seen that the field operator phi of x is given by the form d cube k over 2 pi cube 2 omega a k e to the power minus I k dot x plus a dagger k e to the power I k dot x. And in the last lecture we have seen that these a k's and a daggers are respectively the annihilation and creation operator. We have also defined the vacuum which is annihilated by all the a k's, this equal to 0 for all k, and the creation operators acting on the vacuum give us one particle states which I have denoted as k. These one particle states are eigenstates of the Hamiltonian as well as the momentum operator with eigenvalues omega and k respectively. So, these are one particle states and similarly you can construct multi-particle states by acting number of a daggers on the vacuum, a dagger k n. This will give you k 1 to k n, and we have also seen that these particle like excitations actually obey Bose-Einstein statistics. So, this represents bosons. So, the field excitations of the Klein-Gordon excitations of the Klein-Gordon field are the bosons. In today's lecture, we will discuss some of the implications. One of them is causality. Causality basically says that if you have two events which I will say, let us say one of them is x, another is y, if these are two events which are separated by space like distance from each other, then if you consider an operator at the space time point x and you consider another operator at the space time point y, then measurement of one of the operators will not affect the measurement of the other operator. So, quantum mechanically what should you do? The commutation of these two. So, you consider any operator at x, any other operator, any other measurable quantity, any other observable at y. If x and y are space like separated, if x and y are space like with respect to each other, then the commutation of phi of x, the operator, any operator at the space time point x with any other operator at space time point y must vanish. The simplest one is the observable phi of x. So, if phi of x and if x and y are space like, then especially phi of x must commute with phi of y if x and y are space like with respect to each other. So, let us see, we have already got the expression for phi of x by solving the Klein-Gordon equation. We can put this expression for phi of x here and then derive this commutation relation and then we can see that they in fact commute. So, let us consider the solution for phi of x, which is look at the time dependence here. Here the time dependence comes like e to the power minus I omega t, whereas here it comes with a plus sign e to the power I omega t. So, this part here involves the positive frequency modes, whereas the second part in the expression for phi involves the negative frequency components. So, this involves the positive frequency components, whereas this one negative frequency we will denote this to be phi plus of x and this one to be phi minus of x, so that it will be convenience for us to do the computation. So, let us represent this to be phi plus x, whereas this to be phi minus of x. Phi plus x involves only the annihilation operators, whereas phi minus x involves only the creation operators. So, phi plus x will commute with phi plus y, and also phi minus x will commute with phi minus y, whereas phi plus x may not commute with phi minus y, and the vice versa. So, we can try to evaluate this commutator and express it in terms of phi plus x and phi minus x. When we do that, what we will get is the following. So, phi of x, phi of y is phi plus x, phi minus y plus phi minus x, phi plus y. If we compute the first term here, we can obviously get the second term just by interchanging x and y and a sign. So, what we will do is that we will first evaluate this commutator of phi plus of x and phi minus of y. What is this commutator? For phi plus x, we will use the variable k d. So, you have dq k over 2 pi cube to omega, and for phi minus y we will use the variable k prime. So, I will have dq k prime over 2 pi cube to omega prime as the integration measure. Then I have e to the power minus I k dot x from phi plus of x and e to the power plus I k prime dot y from phi minus y, and then I have the commutator of a k, a dagger, k prime. We already know what this commutator is. So, we can put the value of this commutator here. This commutator we have already evaluated, and then this is 2 pi cube to omega prime delta k minus k prime. So, you can substitute this for the commutator, and then we can see that this 2 pi cube 2 omega prime will cancel with this 2 pi cube 2 omega prime. We can integrate out one of these k primes variable. When we do that, what we get is d cube k over 2 pi cube to omega times e to the power minus I k dot x minus y. Okay. This is the standard notation. This is represented by something which is known as delta plus. This is equal to minus I delta plus of x minus y, where the function delta plus of x is defined to be I d cube k over 2 pi cube to omega e to the power minus I k dot x. So, we have already evaluated the first term. The second term will simply be phi minus of x, phi plus of y is simply minus phi plus of y, phi minus of x. So, this is minus, sorry, the standard notation is such that there is an I here. So, there is a minus I in the definition of delta plus of x. So, this is minus I delta plus of y minus x, which is also denoted as I delta minus of x minus y. When I substitute that in this expression, what I get is the commutator of phi of x with phi of y is I delta plus of x minus y plus I delta minus of x minus y, which is defined by I delta of x minus y, where delta of x minus y is delta plus of x minus y plus delta minus of x minus y. When I substitute the expression for delta plus and delta minus, what I get here is I times d cube k over 2 pi cube to omega e to the power minus I k dot x minus y minus e to the power I k dot x minus y. All right. There is a minus I here. Thank you. So, when I substitute it here, I will get this commutator here to be the one without a factor of I somehow I am missing a factor of I somewhere. Okay, I think it is fine. So, because of this minus sign, you can express this delta of x minus y as also a sign. You get a minus. So, when you add this, what you get is minus 2I sin k dot x minus y. And hence delta plus x y, this I will go away, and then you can see that this involves integration of dqk over 2 pi q to omega times 2 sin k dot x minus y. So, this delta of x minus y has several properties. First thing is that it is an odd function of x minus y, it is an odd function of its argument because sin is an odd function. Second thing is that it is Lorentz invariant, and finally, we can show that this in fact satisfies the Klein-Gordon equation when the argument is not 0. You can apply the Klein-Gordon operator on this delta of x minus y, and then you can see that it in fact satisfies the Klein-Gordon equation when this is non-zero. However, we would like to show that this commutator in fact vanishes when x and y are space-like with respect to each other. Okay? Or in other words, we would like to show that this delta function actually becomes 0 when x minus y is space-like. So, let us do that. You know, if you consider a quantity which is Lorentz invariant, and if this quantity is 0 in one inertial, in some of the in any one inertial frame, then it will remain 0 in all inertial frames because of Lorentz invariance. So, we will exploit that property, and then we will go to a frame where we will compute this delta of x minus y to be 0 if x minus y is space-like, and then this will tell us that it always remains 0 as long as x minus y is space-like. Since Lorentz invariant is so crucial, let me prove that this delta function is in fact Lorentz invariant. So, this is d cube k over 2 pi cube to omega times the minus I a to the power minus I k dot x minus y minus e to the power I k dot x minus y. This is already Lorentz invariant, this is also Lorentz invariant. I have claimed earlier that this integration measure here is Lorentz invariant. I have not proved it so far. So, let us prove that this integration measure is Lorentz invariant. We know d4k, unlike d cube k, d4k is Lorentz invariant. When you make a Lorentz transformation, it will give you determinant lambda, which itself is invariant under proper orthochronous Lorentz transformation. So, this is Lorentz invariant. Delta of k square minus m square, you consider this quantity where k square is k mu, which is Lorentz invariant. Therefore, this is Lorentz invariant. Theta of k 0 is also Lorentz invariant. So, you consider this quantity here, which is Lorentz invariant, and let us evaluate this integration. This is integration d cube k, integration d k 0, where k 0 runs from minus infinity to plus infinity, and delta of k square minus m square is k 0 square minus k square minus m square, theta of k 0. Here k 0 is a variable which ranges from minus infinity to plus infinity. We have already seen that this is omega square. So, let us rewrite this. This is d cube k minus infinity to infinity dk0 and delta of k0 square minus omega square. That is the argument of delta function, and then theta of k0. This theta of k0 restricts k0 to take all positive values. So, you can already see that if you write this k0 square minus omega square is k0 plus omega times k0 minus omega, and you use the property delta of a x is 1 over a delta of x, right. So, then you will see that you can evaluate this k0 integration here, and this will turn out to be d cube k over 2 omega. So, we have started with a quantity which is Lorentz invariant, and then we have carried out the k0 integration, and at the end we got this integration over d cube k over 2 omega. Therefore, this here is this factor 2 pi cube is for convenience. So, this is actually Lorentz invariant. So, we have proved that delta of x is in fact Lorentz invariant. Now, it is very easy to show that this is in fact 0 when x minus y square is negative. You know, if two events x and y are space-like with respect to each other, then you can perform a Lorentz transformation and make them simultaneous. By performing a Lorentz transformation. So, I can set the 0th component of x to be equal to the 0th component of y. Okay. If that is the case, then so I start with delta of x minus y, which is delta of x0 minus y0 x minus y, and I can make a Lorentz transformation such that x0 minus y0 is 0. So, this is also equal to delta of, since delta is Lorentz invariant, this will be equal to delta of 0 x minus y. What is delta of 0 x minus y? This is equal to minus 2 integration d cube k over 2 pi cube 2 omega times sin k dot x minus y, right. There is a minus which will come from sin, and there are two i's which will give me a minus. So, as a result it will be plus. Now, you can see that this in fact is 0, because this is an odd function of k which is integrated throughout the entire range of k. Therefore, you can change k to minus k, it will give a minus sign, and hence this will become 0. This is 0 because of the fact that the integrand here is an odd function of k. This is not the case when the argument here is not 0. Okay? If you cannot make this to be 0, then you do not have a you have a 4 vector product here in the argument of the sign, and it is not an odd function of k usually. So, this does not vanish when you cannot make this argument here to 0, whereas if you can make it to 0 by a Lorentz transformation, then this vanishes identically. So, what we have seen is if x and y are space like with respect to each other, then you can make them simultaneous, and when they are simultaneous, these two events are simultaneous, then the delta function vanishes. So, the delta of x becomes 0, delta of x minus y becomes 0 if you make the argument simultaneous, and they are simultaneous if they are space like with respect to each other. So, the conclusion is that this delta here vanishes if x and y are space like with respect to each other. Since this delta of x minus y is up to a factor of I equal to the commutator of phi of x and phi of y, therefore, phi of x and phi of y commute when x and y are space like with respect to each other. This is what causality tells us, and hence we have seen that at least the Klein-Gordon theory is causal, in the sense if two events are space like with respect to each other, then the measurement of an observable at one of these events does not affect the measurement of any other observable at the other space time event. Now, we will start with this commutator . Right. And we can show that this actually is a green function of the Klein-Gordon operator. How can you do that? The Green's function for Klein-Gordon operator can actually be obtained by solving this equation del square plus m square phi equal to I delta of x minus y. And the solution here, if you write phi of x minus y to be d4k over 2 pi 4th e to the power minus I k dot x minus y f of k, you can substitute it here, and when you substitute it here, you can see that f of k is in fact 1 over k square minus m square. It is very straightforward. This delta, you can have the integral representation for this 4-dimensional delta, which is same as this without this factor of f of k here. So, you can see that this in fact when you operate del square over m square here, you will get a k square minus m square in the left hand side. So, f of k times k square minus m square is 1, and hence f of k is k square minus m square. So, the Green function for the Klein-Gordon operator is I will denote this as g of x minus y is d4k over 2 pi fourth e to the power minus I k dot x minus y divided by k square minus m square. Again, this k square minus m square has a pole when you consider the range of k0. K square minus m square is nothing but k0 square minus omega square, and hence it becomes 0 when k0 is equal to plus or minus omega. So, therefore, the integrand diverges at these 2 points. So, you need to define what do you mean by this integration. You can evaluate it in 4 different ways. So, therefore, if you consider the integration on the k0 line, this represents k0 here, this is plus, this is minus omega, and this is plus omega here. So, this integrand diverges. So, you can evaluate this integration by the means of Cauchy's residue theorem. You need to define what do you mean by this integration. You can do this integration by removing these 2 poles in 4 different ways. One of them is you can in fact consider your contour to be like this, or you can consider the contour downwards here, or you can consider one of them upwards, one of them downwards, and so on. So, there are 4 different ways you can evaluate this integration, and accordingly you will get 4 different answers. So, depending on your boundary condition, one of these integrations will be the correct integration. Or what you can do is you can adopt this epsilon prescription, and then you can consider this integration to be the limit epsilon tends to 0 plus integration d4k over 2 pi 4 times e to the power minus I k dot x minus y divided by k0 plus I epsilon square minus m square. You can consider k0 minus I epsilon also. That will tell you that you are choosing a different contour and so on. So, this is one particular way of choosing your contour. What we can do is that we can evaluate this integration here, and then this will be equal to the commutator phi of x, commutator of phi of x and phi of y under certain condition. So, let us see that. So, let us consider this integration limit epsilon tends to 0 plus d4 k over 2 pi to the power 4th e to the power minus I k dot x divided by k0 plus I epsilon square minus omega square, right? Thank you. Omega square. So, this here I can write it as 1 over 2 omega times 1 over k0 plus I epsilon plus minus omega minus 1 over k0 plus I epsilon plus omega, right, and I will substitute it here. When I substitute it here, what I get is this d4 integration, I can write it as integration over d cube and dk0. So, this is d cube k over 2 pi cube and 1 over 2 omega, then integration dk0 over 2 pi, then this quantity here times e to the power minus I k dot x times 1 over k0 plus I epsilon minus omega minus 1 over k0 plus I epsilon plus omega. Now, the value of this integration depends on whether x0 is positive or negative. If x0 is positive, then you can in fact show that you can. So, what is the argument here? E to the power minus I k dot x, which is e to the power minus I k0 x0 plus I k dot x. If so now what you can do is that you can consider the integration here on the complex k0 plane, and you can choose this contour of this integration to be this one. This is a semicircle of radius r, and this is the origin, and this runs this here k0. This is complex k0 plane, and in this plane this is your origin. This point here is minus omega, this point here is plus omega, and this is minus r and this is plus r. You choose this contour, you consider this integration on this contour, integration d k0 over 2 pi times e to the power minus I k0 x 0 1 over k0 plus I epsilon minus omega minus 1 over k0 minus k0 plus I epsilon plus omega. You choose this contour integration where your contour C is this one, and you take the limit r goes to infinity. Okay? And you can see that this contour here, if x0 is positive, okay, then this contour will in fact be equal to the integration minus infinity to infinity, the same integration where you take, instead of choosing this integration along the contour, you take it from minus infinity to plus infinity. That is because if x0 is positive, then the integration along the semicircle actually becomes 0. It becomes exponentially small, and in the limit r goes to infinity, this in fact vanishes. On the other hand, if x0 is negative, then the contribution from this semicircle does not vanish. So, this is not equal to this when x0 is negative. This integration along this contour is equal to this integration where k0 varies from minus infinity to plus infinity only when x0 is positive, because only then you can see that you can take k0 to be some I r, and then this will give you some e to the power minus r x0, and in the limit r goes to infinity, this contribution from the semicircle in fact vanishes. On the other hand, if x0 is negative, you will get plus mode of this. So, this diverges, therefore, this equality does not hold. In fact, if x0 is negative, you can choose the contour the other way. You can, instead of closing it from the down, you can close the semicircle from up, and then the other integration here from the semicircle on the upper half plane vanishes. So, now you can see that this is in fact equal to dk0 over 2 pi e to the power minus I k0 x0 1 over k0 plus I epsilon minus omega k0 plus I epsilon plus omega, provided x0 is greater than 0. Now, the reason I am considering this contour here is I can evaluate this integration using Cauchy's residue theorem here. Therefore, I have evaluated this integration when x0 is positive. So, what is the value of this integration when I use Cauchy's residue theorem? This in fact is 2 pi I times, there are 2 poles, and then you can just add the residues at both these poles. E to the power minus I omega x0 minus e to the power I omega x0, right. This is what you get here divided by 2 pi. So, this I considered without this factor of I k dot x here. When I have I k dot x, I will have an additional e to the power I k dot x. So, I can substitute this in this integration here. When I do that, what I get is there is an I, because there is a 2 pi I in the residue theorem, and then e to the power I k dot x times e to the power minus I omega x0 minus e to the power I omega x0 for x0 greater than 0. What is the value of this integration for x0 less than 0? we can again use the residue theorem. We can choose this contour instead of the contour where the semicircle is in the lower half plane, and the contour this the integration on this contour will be equal to this integration if x0 is negative. But this contour, the interior of this region does not include any pole here. So, the contour integration here is 0. Therefore, this integration here is 0 for x0 less than 0. Okay? Now, this one you can rewrite it here, you can do a simple rewriting, and then you can show that this in fact is equal to the commutator of phi of x with phi of y. I will show this in a moment. So, this you can consider this integration here. This is d cube k over 2 pi cube to omega I. Let us consider this for x0 greater than 0. What you can do is you can take this inside here, and then this simply becomes e to the power minus I k dot x here, where k0 is omega, whereas in the second part you can change this integration variable here from k to minus k. Nothing will change here because this limits are such that this will remain invariant, and here what you will get is omega x0 minus k dot x, which you can write as e to the power I k dot x. All right. So, this entire thing here you can write it in a Lorentz invariant fashion, and you can see that this is nothing but I times the commutator of phi of x and phi of y. So, the green function, what we have seen is that the green function of Klein-Gordon operator is equal to the commutator of phi of x times phi of y, provided x0 minus y0 is 0 and this is 0 if x0 minus y0 is less than 0. So, just to summarize, what we did is we evaluated this, and then we have shown that this is equal to I times theta of x0 minus y0 times the commutator of phi of x and phi of y. All right. Okay.